And I'm very happy to announce our today's speaker, Professor Tao Su from the Yale Mathematical Center, and he will tell us about dual boundary complexes of Betti moduli spaces over the punctured sphere. Let's welcome.
Okay, thanks. It's my pleasure to give a talk here. And okay, so let's start. The talk is about a problem motivated from like some part of a geometric Pico-Stapler conjecture. So that's why I include section 1 as some motivation. Okay.
So what's the conjecture?
Geometric Pico-Stapler. You will see.
Okay.
Okay, so now I will start from the motivation. So this basically says the following. Let's take C to be a project curve of C with possible punctures. And G here will be, say, GLN or SLN of C. Or more generally, you could take G to be a linear algebraic reduced group. And then let's get MB, some Betti modular space of G local systems of C with certain additional data around the punctures, and M dot is a double modular space of G Higgs bundles of C, again with some additional structures around the punctures. So since this is just some motivation, I will be like very vague. And then by non-abelian Hodge theory.
I'm not quite sure that all people here know the definition of Dolbeault modular spaces. Okay.
It's just some modular space of G Higgs bundles. For example, take G to be Gn. Then the modular space just the modular space of Higgs bundles of rank n.
Higgs bundles, well, also not.
Okay, a Higgs bundle is a pair. One which is a say G equals Gn, then you have a rank n algebraic vector bundle of the curve.
Yeah.
And then plus a Higgs field. Okay, maybe. One second. It's a vector space. We call it E SIP, where E is for G equals GLN, rank n algebraic vector bundle of C, and SID is a morphism from the vector bundle to the vector bundle twisted by the canonical line bundle of C. Equivalently, this means C is just H0C of endomorphism of E twisted by the canonical line bundle. It's just a holomorphic one form. of taking values in this endomorphism sheaf. Okay, is it
Okay.
okay?
Okay.
Anyway, this is just motivation. So
Okay.
even if it's unclear, it's okay. You only have to get like the rough idea. Why do I care about the dual boundary complexity, something like that? Okay.
Fine.
Okay. So then non-abelian Hodge theory says that you have a real analytic isomorphism between the two modular spaces. And then you can put back to get the morphism and the cohomology.
So what is NaH?
Huh?
What is NaH?
NaH, sorry. NaH is, oops. Non-abelian Hodge theory.
Okay.
Okay, so now we have an isomorphism and the cohomology of the two modular spaces. But the point is that this phi is not algebraic. So in particular, phi star does not preserve the mix. Oops. Hodge structures, which are denoted by MHS. This is like a generalization of the classic Hodge theory for smooth projective variety, or if like smooth projective complex manifold. In classic Hodge theory, then you just have a Hodge decomposition. And this is a generalization of this Hodge decomposition to any algebraic variety, not necessarily smooth, not necessarily compact. So because, and it's essentially algebraic geometry. So then the natural question to ask is, how does the mixed Hodge structure and the cohomology of the Betti modular space look like? And the both side. This means you just, by the way, note for the Betti modular space, the mixed Hodge structure is of a so Hodge type. So then surfaces to look at the weight filtration. If you don't know what a weight filtration is, it's okay. I mean, in the next two sections, it won't appear. Anyway, it's just encoding mixed Hodge structure and this cohomology. It just gives a filtration of the cohomology. Okay, this leads to the so-called cohomology Pico-Stapler conjecture. To answer this question, it's a conjecture by Cataldo, also and Migliorini, which says that, okay, if you take the weight filtration, it corresponds to end-of-phase law, reverse filtration. Up to some maybe dot prime, maybe simulation. So what is P? P is the perverse filtration and the cohomology of the double modular space with respect to the Hitchin map. Again, it's just the perverse analog of the wave filtration. Whenever you have a map between two topological space, then you can have a low spectral sequence converging to like the core module total space, and this is the analog of that. Well, the point is, okay, so left-hand side is sort of structure coming from attribute geometry, and the right-hand side is something about the topology of this Hitchin map. And the conjecture would answer the question. Okay, so, but then, since this is a conjecture about the cohomology, we really want like some kind of geometric interpretation. And the moral answer is a so-called geometric Pico-Stapler conjecture. And morally, we start from the following. We take firstly the Betti model space, and then you can take some low compactification. This means you have a smooth projective variety with the boundary divisor, which acted by partial MB minus MB. This is a boundary divisor with the boundary divisor a simple normal crossing divisor, something like this. And actually we can actually may assume, but like resolution of singularities, the intersections of irreducible components of the boundary divisor are always connected. This is basically done by like resolution of singularities. So I can take this to be, say, the union of finite many irreducible components. And each one of which intersect with each other transversely. So then we can define the dual boundary complex, which is part of the title. Says the following. It denoted by the D partial MB. This is a priori a simplicial complex such that the vertices, say I, correspond to the irreducible components. And say I have a few vertices I0 up to IS spans a S simplex if and only if the intersection of the corresponding irreducible components is non-empty. Why this is something useful? One, the dual boundary complex is a invariant of the Betti modular space. Actually, this works for any irregularity in the sense that up to homotopy equivalence. Two, the homology of the dual boundary complex captures information about the weight filtration and the cohomology of the model space. More precisely, it says the following. You take the reduced homology of the dual boundary complex, then it's canonic isomorphic to some. So you have weight filtration, then you can take the associated weighted piece and the degree 2D of the cohomology is 2D minus I, something like that. And D here is just the complex dimension of this model space. So you see the dual boundary complex does encode some information about the mixed structure of the Betti model space, which is like the left-hand side of the picoscopic conjecture. Not all of them, but like some information. So now let's just have like some easy examples. First, take M equals C star. This is a viewed as irregularity. I take a compactification, just take the inclusion to P1. Okay, so the boundary divisor is just 2 points, right? Then what is the dual boundary complex? It's just 2 points, right? Because you only have a simplicial complex by definition. You have 2 points, 2 vertices, and no higher dimensional simplices. So you just get 2 points. So this is just S0 actually. And M equals C. Again, take the inclusion to P1. This is M bar, local complication. Then again, the dual boundary complex is homotopic to just 1 point. And fact, if you have 2 varieties and take the product, I can look at the dual boundary complex of this product, then it's a fact that it's a homotopy equivalent to the following. It's the join of 2 simplicial complexes. And then you apply this fact to the 2 examples above, then you immediately get the following. Dual boundary complex of C star, say, to D. Then you just take S0 D times, and then take the join of them. In the end, you get SD minus 1. Do you agree? And another thing is that if you take the dual boundary complex of an A1 factor, which is C cross a variety, then this is just a point, homotopy equivalent point, because the dual boundary complex of a C is just a point, and you take the join of a point with a simplicial complex, you just get a cone, which is contractible. Any questions so far?
I don't think so.
Is okay?
Okay.
Okay, so now this is like the motivation for the main thing of this talk. There is a so-called homotopy type conjecture due to 4 people. Particle, Mo, Handian, Simpson, which says the following. There is a homotopy equivalence between the dual boundary complex of this Betti model space and the sphere of a D-1, where these complex dimension. So even if you don't understand what a non-abelian Hodge series is, this statement should make sense to you. It's a purely topological statement. You just have a variety and you have some way to define a simplicial complex. And the conjecture says the simplicial complex is homotopy equivalent to a sphere. Why this is interesting? Well, this is part of the geometric P equals W conjecture, again, by the same group of people.
Can you give the best reference to the P equal W conjecture? So the best paper to read about that.
A reference?
Yeah.
Okay, so there is a survey by Orini, something like a recent results in non-abelian Hodge series of curves, which has a less introduction to this subject.
Okay.
Okay, actually, I also mentioned that about this homotopy. Oh, okay, I haven't finished the statement of a pico-static conjecture, which roughly says the following. There is a homotopy commutative diagram of the following form. Which is roughly so left side, this map, you can view it as the Hitching map at infinity. Okay, and what is this? This is just a punctured neighborhood of infinity. Infinity here just means the boundary divisor in MB.
So is it 2 or is it delta? So the right, so you are writing, is it 2 or is it delta? I think it should be delta.
Alpha.
No?
You mean this map?
Yeah.
I just dropped the map by alpha.
Alpha, okay, fine.
Yeah, it's just rotation. I mean, the dual boundary complex will laterally give such a map from the punctured neighborhood of the boundary divisor to the dual boundary complex up to homotopy equivalence. And then the geometric pico-static conjecture says this is commutative up to homotopy. And in particular, the arrow here, this is the homotopy equivalence is exactly the homotopy type conjecture. And the phi is induced by the non-abelian Hodge map. So the basic point here is that expect morally geometric pico-static should imply most of the common pico-static conjecture. The point is, you already see the dual boundary complex captures like some information about the
cohomology or what? Coherent. From P equals double.
Let me rewrite this. Is that better?
Yes. Okay. Geometric yields homological. Okay.
Yes.
Okay.
I'm not going to like say anything more than that. This is the motivation.
Okay, fine.
So main thing for this talk, in this talk, will be the homotopy type conjecture for wild characteristics to wild characteristics or I will just say it's a irregular generalization of the previous modular space. Actually, I only care for the moment. I only just consider C to be CP1. Okay, so let me first state the theorem. Says the following. Oh, actually, the same one. Sorry, let me say one more thing before that. So, what is this? By the irregular Rimann correspondence, this says that the modular space in this case is just modular space of constructive shapes and the curve C with micro support or singular support controlled by
Well, when you stop your, so now you're talking about motivation, or are you talking about your theorems? So when you start theorems, I want all definitions to be exact and all formulations to be exact. So for motivation, it's okay.
This is not sentence for the motivation.
Okay.
Controlled by Stokes legendaries at the punctures. Okay. So then basically I will just talk about the modular space of a constructor shapes and CP1 with certain condition at infinity. Okay, Simon. It will be a say n strand positive braid. Example, it is just sigma 1 squared n equals 2. This just says the following. Sigma 1 cubed. Okay. Then this will define for me a Stokes legendary. This will be the following. Funny notation here. So example. I will just use the example above. Then square means I have this beta is a braid, and I compose this with a full twist.
Stokes Legendrian, or so what? Stokes?
Stokes Legendrian, yes.
Yes, but well, I don't understand. Is it a noun or is it an adjective? Stokes Legendrian.
Is that better? Yes, it's a noun.
Okay.
And then you get a 2, 5. It's sigma 1 to 5 actually in this case, right? And this circle means you take the cylindric closure. That. Okay, then this will be the following. This will be my stock Legendre living. This is a form projection. Okay. Form projection of A of the Legendre, not in this case, and lives in CP1, which is C here. Let's say this is somewhere infinity. And this is 0. So this will be Legendre lives in the co-sphere boundary or unit co-tangent boundary of this Riemann surface. Okay. And then this will define for me a Betti modular space with a full notation. 1 infinity beta delta squared and the symmetric closure. This is a Betti modular space. I will consider. And then the homotopy type conjecture holds for this model space. Okay, this is the statement of the theorem. But apparently I have to explain a few things before you can understand the statement. The key point is, what is this? What is this model space? And okay, so then, any questions so far?
Well, so let's see. We have just a classical braid with no further structure, and you want to enrich your structure by getting something Legendrian, right?
Yes, exactly.
So you want to construct a Legendrian knot out of a classical braid.
Yes.
Fine.
Okay. Let's go to section 2. Micro suppose and construct sheaves. So firstly, what is a micro support or singular support? Now I have say F is a constructor sheaf and C constructor sheaf here means I have a complex of shapes of K model, perfect, actually, perfect K modules. So I could take, say, K is like some base field. Then perfect means finite dimensional. Okay. Constructive, such that if restrict to a stratification is locally constant for some nice stratification. Of C. Okay, so basically, this just generalizes the notion of local system. Okay, now I can make the definition. Say I have a point in the cotangent bundle of C, and could say is the co-direction scenario. We say could C is not in the macro support of F if there is a smooth function F and some small ball around X draw smooth function with Fx equals 0 and dfx is just C such that the restriction map of from the following this is like the sections of this space.
So I don't understand. So I don't understand these letters. So is it RI? So what? So is it gamma or R? So you're writing something. So is it gamma or R previous? Yeah. So this I don't understand your handwriting.
This such that there is a restriction map.
Okay. From
this
what?
This is basically the cohomology of this space. Shift cohomology.
Okay, Czech cohomology. Okay.
And to if inverse connected.
So what is it? Ri or what? I don't understand. R gamma. Okay.
Gamma is the notation for global section.
For sections. And R?
R is the derived factor. This is the rat derived. This really is the rat derived factor for this factor. Is the global section. But you may just think of this as cohomology.
Okay.
And maybe a picture here. This is my small ball, okay, and a point X and a co-direction like that. And
so what's the difference between the left part and the right part? R gamma F minus 1.
Sorry, okay, one more second.
So a restriction from where to where?
So delta is a small positive number.
No,
USD.
So is it a map from itself, from R gamma to itself? So I don't see any difference between the
no,
right
this is
part.
okay. I see. This is positive delta, and this here is negative delta.
Ah, okay. Okay, now I see. Okay.
Okay, so now I have two open subsets. And I want to compare the cohomology over this space and cohomology of this space. And the definition says, if this, apparently you have a restriction map between the two cohomology, if it's not a quasi-isomorphism, if such that this is not a quasi-isomorphism, or means isomorphism and cohomology. If it's not a quasi-isomorphism, then we say this C is not in the macro support. So
Okay.
this is maybe slogan. This just says the local sections of F do not propagate along the codirection C. Is this clear?
So who is not in the micro support?
This vector C.
Okay.
And I want to consider all such covectors. Dealing with the support of the sheaf and take a closure. This will be a closed subset in the cotangent part of C.
So intersection or union?
Union.
Okay.
Remember, I assumed in the definition that I only consider covector which is not there. What happens to the case when C is 0? And when C is 0, it's in the macro support if and only if it's in the support of the sheaf. Okay. Fact. This guy is a conic Lagrangian in the cotangent bundle of C. Conic means it's R plus invariant. You have a scaling action in the cotangent fiber, and this shift this set is invariant under such action. Lagrangian here means it could be singular Lagrangian. And then if I take the intersection with the co-sphere bundle or unit cotangent bundle of C, this content in S star C is then a Legendre submanifold, possibly singular. This then allows me to define the shift category it's the DG category of constructor shifts F.
You say it's a Legendrian. It's a Legendrian, not a Legendrian embedding or what?
Since I take C to be a Rimann surface, then this is just a Legendrian knot.
Okay. Okay.
Is a not plus an additional condition, which basically says in the closed field bundle C, you have the new one form, and you can put back this one form to this set of manifold, and you the pullback of this one form should be 0. Then it's called a Legendre nut. And then I can define the shift category by this Legendre. So okay. It's fixed lambda in this closed field bundle be a Legendre knot. Then I can define this shift category. Construct shifts F and C such that the macro support at infinity, so to speak, just like an intersection of this macro support with the closed field bundle, and you want this to be included in the given Legendre knot. This defines a category fact. But one more thing, sorry. I want to also define a formula. Take C to be a finite subset of C. Example, C is CP1. I take sigma to be just the.
So I don't understand your letter. So C, so what is that?
Let me, sorry, I know it's bad. Sigma. Okay, finite subset, then I can also define another category. This is the subcategory of the shift category consisting of the shift F such that if you restrict this shift to the finite subset, then you require this should be zero. Okay, fact is that this shift category is a invariant, the Legendre invariant. Is a Legendre isotopy invariant of lambda. And once you have such a category, then I can consider modular space of objects in this category. Which is a generalization of the modular space of local systems. Okay, wait, modular space. Moral definition is, okay. First, MB followed by M1 C sigma lambda K. This is the modular, for the moment, it's modular stack actually of objects in another category. I forgot this. I need one more notion to define this. Sorry about that. Microlocal monodromy. This means there is a natural factor from the shift category I just defined.
Okay, so you have an invariant of Legendrian knots. So can you give any pair of Legendrian knots which have the same topological data and which can be detected by your
Sorry,
invariant?
I didn't get the question. Can you say that again?
Well, my question is, can you, you have an invariant of Legendrian knots. Do you have any topologically equivalent knots so that your invariant can detect their Legendrian non-equivalence? Well,
you want to get topological, not invariant?
No, I'm asking you whether, Legendrian not invariants, we have topological invariants, and we also have Maslov number, Bennikin number, and actually these are classical invariants.
You
So
want to ask about
you construct an invariant. So is it topological or is it more sophisticated?
It's not a topological. It's a very strong invariant actually.
Strong. So okay. So give me a couple of Legendrian knots. Then you have.
Okay.
So can we calculate your invariant?
Yes, you do. For example, you can count the objects in this category. If you take, okay, maybe let me make a remark then. Remark. Take K to be the field of Q elements, then can count number of objects in such a category. C sigma K, and then you get enumerative Legendre isotopy invariant. Example, can recover the ruling polynomial in this way.
Which polynomial?
Ruling polynomial.
Boolean. Okay.
Okay, it's a Legendre isotopy invariant. If you know what is like the Legendre contact homology is.
Do you mean Chekanov-Eliashberg? Yes, we know, and maybe anything else.
Maybe I just didn't get the question. And actually, okay, maybe one more remark. One more remark, then. Oops. What is this? I will just ignore that. Okay. And there is also some remark too. For the moment, we consider complex of shapes, but there is also a two-graded version, which means the more two-graded version of ruling polynomial is topologic. Means you actually recover like coefficient of the Humphrey PT polynomial of the underlying topological knot. Does this sound answer like a little bit of your question?
Okay. So do you have any generalization of a Humphrey by using rulings?
I don't think so.
Mm-hmm.
I mean, well, even if you like have some generalization of the ruling polynomial, it's usually the logically isotopy invariant. It's not topologic.
Okay.
Okay. Okay. Let me come back to the definition. Microlocal monotony. There's a factor to the category of local systems. And this says the phoneme morally. So what is this local system? Look at the stalk at the point in lambda. This is morally the cone of R. If you still remember what R is like the restriction map in the definition of a macro support. Anyway, the point is then I can define the category C1, C sigma lambda K is just a pullback. This is a subcategory of the previous shift category. And I can take the trivial local system and then take the pullback. This defines another category. And again, it's a invariant. And then I can define the Betti modular space here. Modular of objects in this category. This is the modular stack for the moment. but then you can pass through the coarse modular space. Now you get actually a variety of this. This will be the so-called Betti modular space in this talk. So if you think a little bit about this, what it says that originally the Betti modular space of a Riemann surface is just the character variety. It's just modular space of local systems. And now you define a Betti modular space just should be a modular space of like constructor shapes, which is like a natural generalization of local system. And it actually includes, like, for example, the wide character varieties of a punctured Riemann surface. Okay. This is section 2, 3. Okay, now I want to take the example I started with. In general, the argument, the strategy works for, in general, beta is unstrand, party, right? I will just take this example. And then remember I had the Stokes Legendre, which is for the moment, so it's just, we don't have any concrete example. Now this is the one. So the one is infinity 0. So usually this Legendre is draw like this. The hair here, the hair corresponds to the co-direction. Remember the co-direction. Okay. The point is that any shift in this category I define now is let's go. So this is equivalent to the following data. I take the following equivalent. So this front diagram induce a stratification for this Riemann surface, and in this way I get the following picture. This is we call that B, and this is 0, 1, 2, 3, 4. So then I get the equivalent. We call it Q circle. B 0, 1, 2, 3, 4. And is equivalent to some representation of this quiver, such that F is the following: K to K square, K, 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 K.
Representations of what?
You have a quiver?
Well, I don't understand what you are writing. F is a representation of what?
You mean this F? F is just, okay, let me rewrite this. Just, it's an equivalent description of the shape. Let me again just write that down.
Representations of what?
Of this quiver.
Okay.
So this says that such a shape corresponds to the a representation of this quiver. It's like 1, 2, 3, 4, 5. 5 one-dimensional vector space inside a two-dimensional vector space, such that the LIs are injective and Li plus 1 are transverse to each other. Okay, and this is also equivalent to the following. I replace L0 by the co-column. Satisfies pi is surjective and Li injective, and it's a similar condition. Well, the point is this is also equivalent to a shift in another category. The following picture. This is a rainbow closure. Again, in the same space. So this is infinity. And how do I get the quiver? It's like that. K square here, K here. This is pi. And add some dashed lines. This is bad. This is my quiver. This is exactly the picture about. Well, the point is that it's the proposition of the Shendy-Truman-Taslow.
Excuse me. is it an invariant of any Legendrian knot or only of a specific type when you consider some closure of
any positive break.
So you don't have an invariant of arbitrary Legendrian knot, right?
Sorry?
So you don't have an invariant of arbitrary Legendrian knot, right?
It's because no, you can define the shift category for.
So I'm asking you yes or no. Do you have an invariant of arbitrary Legendrian knots?
Yes.
Okay, but not every knot can be encoded by a positive braid.
No.
So how do you get an invariant of an arbitrary Legendrian knot?
Again, the point here I only defined the shift category. No, I defined the shift category for any Legendrian knot, right?
For any. But you said that you use only positive ones.
Oh, for the last section, I only use the positive ones because I want to restriction. I want to look at some nice modular spaces, which are analogs of Betti modular spaces in non-abelian Hodge theory. I don't want to like consider any Legendrian knot. For example, if you look at the web character variety, it's encoded by some Stokes legendaries. They only correspond to like some special legendaries, not all of them.
Okay.
May I continue?
Sure.
Okay. So now I have a shift in this category. Any such a shift has a unique, it's called a low ruling filtration. R.F, which is the following, R0F, which is 0, or 1F, or 2F, up to RNF. And all the RFs are not just shifts, actually construct shift. And C, here is just CP1, such that I can take the associated grid peaks. Okay, of this filtration, which is just the con of Ri minus F to RIF. Then this is called the I shift. Is cross isomorphic to the following form. Let me just take one example. One, two, three. This will be my ice red cusp. And it's a constant shift and this locally closed subset and then extension by 0. So this is what's the point here? This then induces a ruling decomposition. Which is the modular space stack of cost modular space. a decomposition of the modular stack or space to locally closed substacks or subvarieties. So what is this? This is the sheaf in the modular space such that its underlying ruling filtration. So the shape of the filtration is rho. So what is shape here? Shape here is just a normal ruling. Let me just give you one example. So in the working example, NR has 3 elements. I have 5 minutes. Okay. What is row 1? Row 1 is like this. This is my, remember this is my Rimann closure Legendre knot. I have 3 crossings, and I marked this crossing as switch. Then I get a shape of the ruling filtration in the following way. The first S sheaf is now like this. This is S3, and this is K, and E2 row
Do you have a reference to the paper where it's written?
the paper of what? For this?
Do you have a reference where it's written?
Okay. Reference Sandy Truman Zaslov, constructor sheaves, and Legendre knots.
Okay.
Yeah, some part of this paper should contain some description of this ruling filtration. Okay, now you have 3 of them, and I skipped row 2, row 3. It's similar to this picture. Okay. The point is that, okay. Key point. Understand, understand, no, it's, the point is, okay, the strata of this decomposition is somewhat simple. It means that you have a let me use the cost model space instead. Has a map to some torus. S rho is an index minus n plus 1. S rho is like the number of switches. And this is a iterate iPhone bundle. Why this is useful to me? Okay, and this is like 1 and 2 is there is a row M in the set of shapes of a Rimann filtration such that its maximum in the sense that MP rho M is not actually K star S rho M minus N plus 1, and this is then K star to D, where D is the complex dimension of the modular space. And 1 and 2 then implies the dual boundary complex of this modular space is actually the same as the dual boundary complex of this maximum piece, which is SD minus 1. Since I had 0 minutes, so I didn't have time to actually compute this example for you, but you can actually, with this example here, you can actually do the computation and check indeed. So example, when CCP1, sigma is infinity, and beta is sigma 1 cubed, and n is 2, then you actually can compute the dual boundary complex is the same as dual boundary complex, the maximum piece is, which is C star Q, no, sorry, C star squared.
Okay.
Which is D minus 1 is S1. Okay, maybe I can stop here.
Okay, thank you very much for a very interesting talk. Well, it would be nice to discuss Legendrian knot invariants in more detail.
Okay.
Thank you very much. And are there any questions or comments? Remarks, maybe? Well, if it's not the case, so let's thank the speaker. The talk was very interesting.
Okay, thank you.